Professor Cook, thank you so much for being our guest at the Global Asia Initiative at Duke University. You are a climate scientist working on paleo environment through dendrochronology, or the study of tree rings to understand historical climate. To begin with, do you mind briefly describing what is dendrochronology and how can tree rings tell us about the past climate?
Oh, thank you. Thank you for inviting me to talk. The trees provide a history of environmental and climatic variability in their annual ring widths, typically, sometimes in other parameters from the annual rings. What is excellent about them is that trees are growing over most of the landscape of the continents, not in Antarctica, of course, but the point is that there's a worldwide availability of trees that can provide environmental information on trees. On climate. What I would like to do is to present a few slides just introducing dendrochronology. I think that will help clarify the value of tree rings as indicators of past environmental change and climatic change. So as an introduction, I'm going to talk about trees as indicators of past climate. And without too much hyperbole or exaggeration, I can say that tree ring records provide the most temporally precise and spatially detailed reconstructions of past climate covering the last several centuries to millennia. They're annually resolved, exactly dated, and can be directly calibrated in terms of the climate variable being reconstructed, whether it be rainfall, temperature, drought, stream flow. And this really sets tree rings in a unique position in paleoclimatology because many of the paleoclimatic records, as good as they are, do not have precisely dated annual resolution. And therefore, it's not easy to directly calibrate them against instrumental climate data. And trees can also live for hundreds or even thousands of years. The oldest living tree in the world known currently is over 4,800 years old. A Bristlecone pine growing in the White Mountains of California. So the fact that these trees have such a long record of environmental and climatic history in the ring widths means that, in effect, they're acting as time machines for telling us what the climate of the past was like in ancient times for climatic and cultural interpretation. There are certain foundational principles that I'd like to just briefly go over in terms of dendroclimatology. We go through a process called cross-dating, in which each annual ring is assigned the exact calendar year of its formation. And this is what I call the gold standard of geochronology. Replication. We are lucky in the fact that we can easily sample many trees at a given location. And we call that replication. It's a collection of multiple samples from trees influenced by the same growth limiting factors in the same macroclimatic environment, be it on the top of a mountain or in a valley or such like that. And this is what enables cross-dating because you can compare patterns of wide and narrow rings from tree to tree. And it also provides direct measures of chronology uncertainty to be made. Cross-dating and replication then enable tree ring chronology to be developed for climatic reconstruction based on calibration directly against instrumental climate records, which provides a measure of reconstruction precision, but not a lot about reconstruction accuracy. And therefore, we go through a whole process of validation or verification in which we compare the tree ring estimates of past climate against withheld or independent records of climate variability. And this provides us with a direct measure of reconstruction accuracy of the climate estimates from tree rings.
Sorry for interrupting you a little bit. Do you mind to go back to the previous slides? Do you mind to explain a little bit between precision and accuracy in this context?
Well, the classic example is a dartboard in which one is trying to hit the bullseye of the dartboard, meaning that you are as accurate as possible. You're trying to hit the bullseye, and that's the measure of precision. When you hit the bullseye, you're exactly precise. You can have a cluster of darts sitting significantly away from the bullseye that are clustered very tightly, but in that sense, the cluster of darts are precisely aligned with each other, but they're highly inaccurate because they're far away from the bullseye. Whereas accuracy reflects the fact that the answer you're getting or the location of the dart is exactly where it should be with respect to, in this case, the past, what the trees are telling us about the past. And that's what we mean by accuracy. In a statistical modeling perspective, we can estimate very precisely a relationship between tree rings and climate, but there's always a danger of what we call overfitting. By that, I mean that the least squares methods that we typically use, not always, but typically, have a tendency to create a overly precise estimate of what you're actually trying to reconstruct. And only by comparing the measurements as precisely estimated as possible against withheld data not using the calibration exercise are we able to determine the degree to which the actual values reconstructed in the past are accurate, close to the bullseye, as it were.
I see. Thank you so much for explanation. Please go ahead.
Just quickly, the principle of cross-dating is very nicely shown in this photograph provided by Connie Woodhouse at the Tree Ring Lab in Tucson. And it shows the way in which we align the annual ring widths from tree to tree in a way that effectively guarantees that we are assigning the correct annual year to each annual ring. Here's, for example, here's a very narrow ring in 1925, shows up here, and it's very narrow here. There are times when these very narrow rings can actually be missing from individual wood samples. And so if we were just kind of counting back in time and assigning annual years or dates to the rings without taking into account that maybe this ring right here was missing from a particular wood sample, we would be off by a year. So cross-dating is extremely important. It is the foundational principle of dendrochronology, dendroclimatology, and without it, we really wouldn't be a science. Cross-dating also allows the extension of tree ring records back in time using living and dead wood. And here's just a schematic, kind of a cartoon example that shows what I'm talking about, where we start out from sampling a living tree, right here, and then we take a sample of wood from a dead tree, and also from maybe timbers from an ancient dwelling, and we match the patterns of rings that overlap between the different samples. If we know from a living tree the exact annual years of formation of the tree ring series, because the tree is living, then we can use that process of cross-dating to lock in exactly the timing of when the timbers were cut, for example, for this archaeological dwelling, or from this ancient dead tree. And this is what enables us to push the records back in time, thousands of years in some cases. Just an example here of exact tree ring dating in action. Here's a fire-scarred tree, sugar pine from California, showing the dates of fire scars. Without cross-dating, we would only be able to guess when these fire scars happened, or these fires happened that produced the fire scars. So this shows, in fact, that the timing of the formation of these scars. And what's important here also is the fact that the timing of these scars can tell us about the climate of the time that was conducive to causing fires that produced these scars. And it turns out the El Nino Southern Oscillation, or ENSO, is very influential in creating the conditions that cause these fires to occur, and in this particular case, cause the formation of fire scars in living trees.
Professor Cook, sorry for interruption. You mentioned before ENSO is very important in understanding global warming or global climate change. So do you mind pause here a little bit and explain what is ENSO?
There's a process in the tropical Pacific called the El Nino Southern Oscillation. It's a process that causes the thermocline of the tropical Pacific to oscillate back and forth on a particular time scale that's typically in the 2 to 7 year period. Right now, for example, we are in a La Nina period, which means that the eastern equatorial Pacific is cold, is colder than average. That causes droughts in North America. And ironically, in a sense, it causes wetter conditions in Asia, in Southeast Asia, for example. And this is the single most important internal mode of climate variability on Earth. The El Nino Southern Oscillation has a larger effect on climate, worldwide climate, particularly hydroclimate, rainfall variability and drought, than any other mechanism on Earth. And it's predictable. There's a good mechanistic model for explaining how this process works in the tropical Pacific. And that model is good enough where it's possible to make at least one season ahead forecast what ENSO is going, or what the El Nino Southern Oscillation is going to be like, what state it will be in, for determining the regional or global impacts of this process on climate.
Thank you so much for the explanation. Please proceed.
The value of tree ring is in how the tree ring records can inform us about past climate. And here's an example from work done in northwestern New Mexico, the place called El Malpais. It's a lava field in northwestern Mexico. And what's notable about this is that the instrumental record goes back roughly to 1850, although that's probably a bit of an exaggeration, probably more like 1900 with quality. But the point is that if you were to look at the instrumental record, you say, okay, well, there's been a couple of severe droughts like in the 1950s, as is shown right here. But it seems that seems to be the worst event. Well, if you do a reconstruction on this long tree-ring chronology developed from there, going back over 2,000 years in time, you find out that, in fact, the modern era has been remarkably wet, in a sense, compared to the past. The record of wetness and dryness is mainly dominated by wetness up until the more recent times. But you go back in time, and there are some massive droughts that are indicated here that are completely unpredictable based on the current climate records available, or based on any theory that would have told us to expect this kind of behavior. So I think this is an example of how tree ring chronology can really, really help us out in understanding what the natural background state of climate variability is, and in a way that may provide ways of improving theories for understanding the way the climate system works for now and in the future.
From your field work study on the tree rings, I know you compiled very extensive atlas or database of global droughts. And what you are showing here, the Monsoon Asia Drought Atlas, is one of the most important ones, since this is a Global Asia initiative. So do you mind to introduce to the audience what is this atlas and how we can use this for other studies?
Yes, just before I introduce the Monsoon Asia Drought Atlas directly, I'm going to describe what drought atlases are and where they kind of came from briefly. And this all began in North America with work I started back in the 1990s, really, in creating what I call here the North American Drought Atlas. And what it is, it's a reconstruction of drought indices based on instrumental temperature and precipitation data that can be reconstructed from tree rings, and in so doing create maps or atlases of variability of wetness and dryness over time. This turned out to be extremely successful in North America. Again, is based on this idea that you take the instrumental drought indices right here in these symbols here and the pluses, and use a network of tree ring chronologies that you see right here to reconstruct each one of these grid points of Palmer Drought Severity Index, as it were. I won't go into the mechanics of doing that, but the method I developed back in the 1990s has proved to be extremely effective for doing this. So remember, in New Mexico, we had this one location here that told us about drought variability. Well, that's all well and good, but really climatologists need to have spatial patterns to evaluate, because that tells them much more about the mechanisms or the forcing mechanisms that are causing the observed or the reconstructed variability that's being produced in these maps. But here's like one of the great surprises from the North American Drought Atlas: a drought of 48 years of duration.
Wow.
Over the period 1434 to 1481, from shore to shore in the United States. If this were to ever happen again, the effect would be absolutely catastrophic. I'm not saying it will, but the point is the climate system has a capacity for doing this, and we don't know why. We don't really know the details on this. In this figure right here, this is looking at the tendency for the area of drought in the Western United States to vary in long-term ways that are quite different from what you see here in the more modern era right here. This helps solidify our understanding of the occurrence of megadroughts in the past that have never been observed in the instrumental record since roughly the 1600s, in North America anyway. So this really woke up a lot of people to the understanding that the climate system has the capacity to generate decadal persistent droughts in ways that, again, the instrumental record cannot inform us about. So with this kind of brief introduction about drought atlases, I'm going to move on now to the Monsoon Asia Drought Atlas. And here's the general domain of the MATA, as produced in 2010 and updated a bit since then. And so I'll be talking about this area right here, okay? To develop the MATA, we need tree ring chronologies in Monsoon Asia. And that was a big challenge, because there really wasn't that much of a network of tree ring chronologies developed there up to where myself and colleagues at the Lamont Tree Ring Lab became involved in. Here's just an example of some tropical pines. This would be in Thailand, I believe, and local helpers or colleagues taking cores of wood from the trees. Now, to be sure, we do not kill the trees that we sample. It's very important to emphasize that. Living trees are typically sampled using an increment borer, this long tube, metal tube with a cutting tip on the end and a handle for turning the borer into the tree. In so doing, you can extract a long dowel-like core of wood from the tree. If you get into the center, it would have the entire life history of the tree, from the bark right here to the inside of the tree. And this has to be done for maybe 10, 20, 30, 40 trees at a given location. Remember, replication being an important aspect of dendrochronology. So when we go in and sample trees in Asia, we sample many trees at a given location. And this is the way we do it. And again, we do not kill the trees. The trees can be revisited years later and resampled. And we sampled multiple species. Each species has its own sort of characteristic expression of growth related to climate. No two species are quite the same. So multiple species can tell us a lot more about climate variability and change in the past than a single species can. Here's one example, teak from, this would be from Thailand, tropical pines again. A great discovery by Brendan Buckley in the central highlands of Vietnam, a long-lived conifer that survived the Vietnam War. It was quite remarkable. The area was never impacted significantly by any of the wartime activities there. This is Phocaenia hodginsii. The point is that it grows for 1,000 years or more. And here's a couple increment cores from Phocaenia, and you get to see all the annual rings here. Wow. They're all telling us something about past climate, among other things, environmental variability, but there's a lot of climate information in them. So this was a massive discovery by Brendan in particular for reconstructing climate in Eastern Asia and Southeast Asia back 1,000 years or more. But we can go to other places in Asia too, High Asia. That's where I did a lot of my work over the years. I never went to Pakistan, but a colleague of mine did. This is in the Hunza Valley of Pakistan, an ancient conifer tree right here, juniper tree, interdate of 826 AD. Over 1,000 years old. Here's a Tibetan Plateau. I was there working with Xiaohua Go at Langzhou University. She's right there. And we cored more of these juniper trees there. Again, very old, very long-lived trees, could be up to 1,000 years of age. Bhutan, the Himalayas of Bhutan. Here's a spruce tree that was over 500 years of age. Down here, this is the more epic trip I ever made in Nepal, eastern Nepal. This is a hemlock, Himalayan hemlock. It's over 1,000 years old, and it took us 13 days trek to reach this tree. So it can be a real experience, shall we say, adventure to find the trees that you want to core that have the longevity to provide the long records of climate variability and change that we want for climate reconstruction. That's me, incidentally, right down here. Back in 1994, so I was much younger then. I couldn't possibly do this trek today. And here's a map. This shows a grid of palmer drought severity indices that I reconstructed. The red little crosses there, and the green circles, filled circles, are tree ring sites developed over Monsoon Asia. Not all of them were developed by the Lamont Tree Ring Lab, I should say. Dendrochronologists tend to be very collaborative, and oftentimes work done by others would be beneficial for the work we were doing. So I certainly give proper credit to many individuals who contributed data to this effort. But this gives you an idea anyway of the way in which we reconstructed the Monsoon Asia Drought Atlas, this network or grid of climate variables or drought indices, and using this network of long tree ring chronologies. Now you might say that, well, gee whiz, there's nothing here. Why is that? Well, the answer is there's no trees there. It's a barren area of Western China. The Taklamakan Desert is located in here, for example. So that's always a problem. Sometimes it wasn't possible to find old trees. Like in India, there's a long history of forest cutting, so it's hard to find trees there too. So this is basically the best we could do at the time. So what can the model be used for? Mapping historical monsoon failures in full spatial detail and determining their associations with cultural change and human impacts. The paper that was produced from the initial Monsoon Asia Drought Atlas was Asian Monsoon Failure and Megadrought during the last millennium, published in Science in 2010. And here are some maps of notable events, you might say, climatic events that could be extracted from the Monsoon Asia Drought Atlas. One of the more notable ones is the Ming Dynasty drought that led to the downfall or the collapse of the Ming Dynasty in the 1600s towards 1650. This is backed up by historic records, I do believe, but there's a significant drought that occurred around the seat of government at a time when the emperor was thought to be divine and would have some way of controlling the fate of China with respect to climate and droughts and things like that. And the drought happened in a way that impacted the people up here, and that led to the eventual downfall of the Ming Dynasty. But there are other periods of odd climate variability affecting cultures in Southeast Asia as well. This is the pattern of drought variability related to the strange parallels drought. Some work done by Victor Lieberman. He had found lots of cultural and archaeological evidence for rapid changes in Southeast Asia in particular, cultural changes that couldn't be explained very readily by like invading armies, things like that, at least not in total. And the work that we did in Asia with the Monsoon Asia Drought Atlas showed that, in fact, this period right here was a 12-year period of fairly intense drought in Southeast Asia. And that fits in very well with what Victor Lieberman found based on investigation of historical records from that area. The East India drought, that's in the 1790s primarily, and the Great Drought in the 1876-78 period. This was largely caused by the El Nino Southern Oscillation. It led to the deaths of millions of people in Asia.
This is also recorded in documents. And I think in this drought, the Qing dynasty probably lost 2% to 3% of its population because
Oh, really?
Yeah.
Oh, boy. Yeah, that's a lot. Yeah. You know, the definition of mega droughts, as I have here, is difficult to pin down because how long does a drought have to be a mega drought? In the Western United States, it might have to be a decade or more in length. These droughts are not quite as long as that, but the point is that they had huge impacts on the local people there. You know, if the drought's severe enough and it's multi-year, whether it's only 3 or 4 or 5 years, that could be enough to really trigger social upheavals and hardships. So now I'm going to go on to one of the more famous bits of work done primarily by Brendan Buckley, my colleague here, on drought and the demise of the Khmer civilization at Angkor in the early 15th century. Here's Angkor Wat, a large temple complex, and this is where Angkor is located in Cambodia, near Siem Reap. This is from a paper that Brendan published with archaeology colleagues. Well, Roland Fletcher, for example, very famous. He's done years of research at Angkor. So when I mentioned Victor Lieberman before, and he wrote this extremely interesting bit of work on strange parallels, as I had indicated before, Southeast Asian global context. And he produced this figure. His investigation seemed to show, here's the strange parallels drought that we reconstructed from the MATA. And he just put this in right here as something that really changed in Southeast Asia, but he couldn't figure out exactly what was contributing to it. It was certainly partly due to climate, we're fairly convinced. And then this whole cultural territorial consolidation, this demise or collapse of Angkor at around this time. And again, this is all great mystery. Well, Brendan's work produced these long records from Vietnam of Phoceania that went back far enough in time to overlap with a period when Angkor was at its peak, entered into his period of decline. Here's a tree-ring chronology at Bi Duc Nui Ba National Park in Vietnam, goes back to 1250. Here are some severe droughts indicated, and they tie in almost perfectly with what's known about the history and the timing of decline of Angkor. So this really piqued a lot of archaeologists and climate historians' interest. And here's what the MATA showed in terms of the scale of drought. This right here is a 21-year drought. So this would qualify even for North America as a mega drought. This is where Angkor is located. And it was just well below average rainfall, a monsoonal collapse, really, for quite a few years. And it happened in 2 pulses, one of them being 1345 to 65, and the other one being 1401 to 1425. And you can see that these mega drought events would understandably have a destabilizing influence on the Khmer civilization at Angkor. And this shows in more detail about the Angkor droughts. This is what to zoom in to this period right here. There's what we call these two Angkor droughts, Angkor 1 and Angkor 2. What's interesting is that they were preceded by what's described as a mega pluvial, an extremely wet period. And there was actual archaeological evidence at Angkor that this happened, and it damaged the hydraulic structures of Angkor. And so the argument has been made that the damage to the hydraulic structures of Angkor by the pluvial actually made Angkor less resilient to the subsequent droughts than it would have been had the damage not occurred. As an aside, there's a famous eruption that happened in 1257-58 around the Indonesia area and Samos. The interesting thing is that the single wettest year of the past 1,000 years over the Angkor area was the year that Samos erupted. It was a massive eruption. It was always a mystery of what kind of climatic influence it might have. Here's evidence that it had big influence on the monsoon, creating catastrophic downpours of rainfall that the hydraulic system at Angkor, for example, was not well set up to receive.
Yeah, it makes sense with all the dust in the air.
Yeah, see, the problem with volcanic forcing is that most people think about how everything is cooler, when the volcanic aerosols block the sun, and therefore they look for evidence of cooling after eruptions. That may be the case for a lot of eruptions, like Krakatoa, for example, Tambora in 1815, 16. But for some reason, and no one, I don't think, really has a good handle on it, Samos was a different kind of eruption. It was considered to be bigger than Tambora, and yet it didn't cause the massive cooling that Tambora did in the Northern Hemisphere. In this particular case, it seemed to have primarily affected, in a very dramatic way.
Interesting.
So there's more we can say about the Southeast Asian Angkor. Neil Peterson and Amy Hessel published a paper in Proceedings of the National Academy of Sciences on the discovery of this Mongol pluvial affecting present-day Mongolia. They identified a period in long tree records from central Mongolia, an extremely wet period from 1211 to 1225. What significance did it have? In a sense, might changing the history of Europe and Asia.
Right.
It turns out that this time period of unusual wetness tied in almost exactly to the major expansion of the Mongol horse army of Genghis Khan. But this was a big discovery that would not be possible without dendrochronology. Well, the Monsoon Asia Drought Atlas provides a spatial context for this same period, 1211 to 1225. We can average the Monsoon Asia Drought Atlas estimates, the maps, and come up with a map showing the average conditions over a much broader area. And here you can see all of Mongolia was wet for that whole period of time. You can see that the wetness extends down in this direction right here. Well, this is almost exactly the trajectory that the Mongol army took as they left Mongolia to invade Europe and so on. It's a horse army. They have to go where the forage is good. They didn't go up this way now. They would have known that it was very dry up here. This is telling us that the Mongol army was following the good forage produced by the pluvial, or good pasturage. And I think this is a new insight into the reason why the army of Genghis Khan left Mongolia the way it did to invade Europe and Western Asia. It could only be possible from tree rings. Another application, this done with Nicola de Cosmo at the Institute of Advanced Studies in Princeton University. And others, there's Amy Hessel. She was on the Mongol pluvial paper with Neil Peterson. Carolyn Leland, she did her PhD work here at Lamont on studies in Mongolia. So there was a big question about the rise and fall of the Uyghur Empire from 744 to 840. Didn't really last a long time, and over in less than 100 years. That the Monsoon Asia Drought Atlas could tell us about the possible influence of climate variability on the rise and fall of the Uyghur Empire. And here's the story, which I think is rather compelling. This is an average of all the estimates of drought over the area of the Uyghur Empire. If we zero in on the time period when the Uyghur Empire existed, you go down here and you see that it basically started during an unusually wet time. Here's cities being established, predominantly wetter than average conditions. And then the area entered into a megadrought period. And with that, the Uyghur Empire collapsed. I think this is one of the more compelling cases for the impact of climate variability on the cultural history of Asia. And move to China now. And how well does the Monsoon Asia Drought Atlas capture severe decadal droughts in eastern China? Here's some work that I came across by Peng et al. In 2014, modeling of severe and persistent droughts over eastern China during the last millennium. And they list in their table 1, 6 particularly notable drought periods. So I went to the Monsoon Age Drought Atlas and extracted drought patterns for those intervals. This is what it comes out from the Monsoon Age Drought Atlas. There's evidence for a severe drought in 1123 to 1152. Not so much in this period right here, although down south there is some evidence of drought. Again, severe dryness down in here in 1353, 1363. This is ill-defined. But here you see 2 very well indicated northern droughts in this part of eastern China. And these agree reasonably well with the work that was provided by Peng. And in fact, if you average together those 6 periods of drought, you can see that, in fact, the Monsoon Age Drought Atlas is reflecting, I think, the occurrence of drought in those periods quite well. And from this work, I extracted the history of hydroclimate variability over this whole general area back 1,500 years in the past. So the point is that there's some very interesting period of variability right here, somewhat extreme. Whether or not this has any link to anything that happened culturally in this part of China, I don't know. I'm not a historian, but the point is that this offers some tantalizing hints that something might be investigated to understand if there was any impacts of, in this case, extreme wetness, and then a period of persistent dryness in eastern China during this time period. So the tree ring reconstructions can actually provide hypotheses that can fuel the research of historians who might not otherwise think of investigating these particular time periods for anything in particular.
This is a period of the transition between the Mongol Yuan dynasty and to the Ming dynasty.
I freely admit that my understanding of Chinese history is very meager. So again, we need scholars like yourself and others like Nicola de Cosmo to help us understand the interface or the linkage, the connections between past climate as indicated by the tree ring data with historical records that are available to be interpreted and maybe linked to past climate show. Then on to this more general climate issues, what causes mega droughts in monsoon Asia? And understanding large-scale climate forcing modes may point the way. And this is where ENSO, the El Nino Southern Oscillation, comes in big time, because there's no question that this process in the tropical Pacific, right through this area right here, has a profound influence on drought and wetness over monsoon Asia areas like around in here. Therefore, we can link the climate reconstructions and the cultural impacts of climate on people in Asia. We can link that to what is going on in the tropical Pacific. Here's just from the Monsoon Asia Drought Atlas. We can look at the predominant, most common mode of spatial variability in the network. So-called empirical orthogonal function analysis enables us to do it. This is the single most important spatial mode of variability in the Monsoon Asia Drought Atlas. And it basically shows up as a very strong dipole between India and interior Asia, north of the Himalayas. And it's a very, very strongly persistent feature. We can use this information right here to project this pattern of variability back in time to produce what we call this projection coefficients right here. And this is what they say, going back 1,000 years. These are megadroughts in India right here. We can then correlate these projection coefficients right here against sea surface temperature over the global oceans. And when you do that, you find out that, in fact, there's a strong pattern of variability in the tropical Pacific and also over the Indian Ocean that's tied to what you see here in the variability due to related to megadroughts. So we can see these patterns right here emerge in a way that tells us what the likely global forcing was on creating these conditions that led to megadroughts in India back in time. And we can then look at another pattern that's also possible to extract from the Monsoon Asia Drought Atlas. In this case, it's a lesser mode of variability. That mode of variability is principally contained in this area right here of China and Southeast Asia. Here's what the projection coefficients indicate back in time. We get into this kind of seesaw pattern of wet Southeast Asia on this side when the coefficients are positive, and dry Southeast Asia. This shows some interesting patterns of variability that, again, can be tied strongly to variations in the sea surface temperatures in the tropical Pacific. ENSO is, as I said earlier, is the single strongest mode of climate forcing, internal climate forcing on Earth. This gives you an example. I've developed multiple drought atlases. North American Drought Atlas, the Old World Drought Atlas, and the Monsoon Asia Drought Atlas here. You can correlate the El Nino Southern Oscillation against the reconstruction of drought at these different locations using the instrumental data and the tree ring estimates. There's a remarkable consistency between what the trees are telling us about drought and wetness related to ENSO variability over on continental scales and what is also indicated in the instrumental data. There's no doubt that the climate information in these drought atlases is extremely important for understanding causal mechanisms of drought and wetness over continental landscapes, but also at local levels, as we saw, say, like the Ming Dynasty drought is a relatively local drought. These drought atlases provide a tremendous resource for understanding the past, both from a climate perspective and also from a cultural perspective. If you notice, there's this white area right here, no drought atlas estimates. And of course, that needs to be fixed. So what I'm working on now is exactly that. And here's what I call the Great Eurasian Drought Atlas, which covers the entire Eurasian continent. I've got a version of it done already, but I intend to improve it. Just to give you an idea as to what's neat about drought atlases, you can create movies. And this actually shows you the interesting pulsating pattern of wetness and dryness over a tremendous continent. And this goes on for 2,000 years. I won't necessarily let it go the whole long time. This area right here will fill in eventually, and so on like that. But this shows the power of the drought atlases, because climatologists need these spatial patterns in order to interpret the causal mechanisms for explaining what they're observing in the atlases themselves.
Thank you so much, Professor Cook, for this very intriguing and amazing presentation about tree rings and all the atlases you have compiled. One question I've noticed, you point out to the gap between the Old World Atlas and the Monsoon Asia. But what about South America?
There, believe it or not, I didn't produce a map to show that, but there is a drought atlas for the southern half of South America. And that was completed a couple of years ago now with my colleagues from South America, and has been published in the Proceedings of the National Academy of Sciences. And even for the eastern half of Australia, there's a drought atlas for that too. So you could say I'm trying to take over the world. I'm getting there anyway. But the thing is, it's hard to do the drought atlas when you don't have tree ring chronologies for the given important areas, and that kind of fills in with time. So that's one reason why you can't just sort of do it all right away. The North American Drought Atlas was completed in 2004. Well, it's almost 20 years since that time. And so I've gradually been building up the development of drought atlases as the tree ring data become available. And that's working out quite well. You just have to be patient,
Sure. Thank you so much. I look forward to that. I think, given time, I probably don't have time to ask you too many questions. So I want to ask you a last question, and maybe
Okay.
the elephant in the room, that's about global warming. So based on the drought atlases and based on the ENSO cycle you have described, where are we in the ENSO cycle right now? And how does this correlate or relate to the global warming we're observing right now?
Regarding the state of ENSO right now, we are in what's called a La Nina state, which is a cold eastern tropical Pacific SST condition. And that promotes drought in the western United States primarily, and wetter conditions in Asia and Southeast Asia and India and so on like that. And the thing that's unusual right now is that La Ninas tend to be short-lived, maybe 1-2 years at most. And I think we're entering into the third year for a La Nina. That's unusual based on lots of instrumental and observational data. I don't think anybody is saying this is an expression of global warming kind of pushing the system that way, but nonetheless, it's happening. The climate models that are used to a tremendous degree of success to model the impact of radiative forcing on climate due to CO2. They're very good at projecting future changes in, say, global temperature, without a question. When it comes to with hydroclimate variability at the scale that we see that on the drought atlases, they have a harder time because these small scale patterns of climate variability or hydroclimate variability are difficult to model mechanistically with by climate models. So that makes it difficult to actually pinpoint exactly how things are going to change with respect to hydroclimate. Some areas better than others, I should say. But it's not a loss. Don't mean to say that at all or indicate that at all, in a sense, model these changes in hydroclimate than it is changes in temperature. Where a lot of the models have a difficulty is in how they model. And so there's a lot of variability from model to model in how well they match the observed pattern of variability in the El Nino Southern Oscillation. Models tend to be more variable in terms of the impact of ENSO on hydroclimate because they tend to be more variable in how well they model ENSO itself. That's a challenge to be dealt with in the future.
I see. Thank you so much for the explanation. Thank you so much, Professor Cook. Thank you for your time today, and thank you for this amazing presentation. I hope we have all learned a lot about the tree rings and what the tree rings can tell us about historical climate.
I greatly appreciate being asked to give this presentation, and I look forward to interacting with you in the future.